Alright, so this is another example of using ease to solve statics problems. This one is example 3.7 in the text. You can see what you have here is this weight that's supported by this boom AO, and the boom is tied up with these cables AB and AC, and then the weight is suspended from point A by this cable AD. And at least initially the cables are parallel to the axes, so you can see AB is parallel to the the y-axis, and AC is parallel to the x-axis. Alright, so they give you some failure criteria. They say that these cables AB and AC can support at most 5,000 pounds, and the boom itself can support at most 8,000 pounds of compression before it buckles. And with those failure criteria, you're supposed to figure out what's the biggest weight you can support with this structure. And then the second part B, says let's move the mounting points B and C, which is basically going to make these cables no longer parallel to the axes. And we'll suspend a 1,000 pound weight, and if that's the case, then determine the forces in the members. So what's the force in the boom, and what are the forces in these different cables? All right, so yeah, I guess maybe go off and take some time and try to solve that, and when you come back, we'll go through the solution together. Okay, so we're going to go ahead and solve this problem. It's actually a relatively easy problem to solve using a computer, and the reason is because we can start the process by setting some arbitrary value of W, and with that arbitrary value of W, it becomes very easy to calculate the forces in these members, and then we can just one by one figure out what value of W causes each of these members to fail. And of course then the value of W that's the smallest is the one that will cause the structure to fail. So let's go through and just derive the equations we need to program, and once we have those derived, we can enter them into ease. So the first thing we would do is enter the coordinates of these points that define the geometry. So the points are A, B, C, and the origin. And then once you have those points, you can define the position vectors that are useful. So the position vectors are RAO, so that's the one that goes along the boom. RAB goes along that cable, and RAC goes along the other cable. And that will define then the direction of these different forces, right? So then we have a free body diagram on point A, and that free body diagram has four forces, right? So there's the force of the weight, of course, and then there's the two forces from the cable, and there's the force from the boom. And then the last part is just to write out these forces. So the force from the weight is known, at least we're going to assume it's known if we specify the weight. So this is just minus W times the unit vector K. So that's the vector force. It has no extra y component, it's only a negative z component. And then we know the directions of the other forces. So FAB is the magnitude of FAB, which we don't know, and then it's in the direction defined by RAB. So the position vector RAB divided by its magnitude gives me that unit vector. Same thing for FAC, and same thing for FAO. So these are three unknowns now, these three magnitudes. But our equation for equilibrium is this vector equation that the sum of these four forces has to be equal to the zero vector. And because there's three components associated with the three dimensions, this is actually three equations. And so we have three equations in these three unknowns, and we should be able to solve. So with that laid out, we can move these equations into ease and solve the problem there. So again, as I said, I'm going to specify the magnitude of the weight to be something arbitrary. So let's just solve it for 500 pounds. And then I am going to enter the coordinates of these points, so A, B, C, and O. So those will be 3D vectors, right? 3D, they have 3 coordinates. So define them as vectors, and then based on this diagram, we can enter their coordinates, right? So A is this point here, it's 9, 20, 12. These are in feet. B is, let's see, this point here, 9, 0, 12. C is 0, 12. I'm sorry, 0, 20, 12, and then O is the origin, so it's just 0, 0, 0. So now that I have these points defined, I can go ahead and use them to define the position vectors. So RAB is just B minus A, RAC is just C minus A, and then RAO is O minus A. And then finally, we'll enter these last sets of equations related to the force. So these forces are vectors. W is the magnitude of W minus the magnitude of W times the unit vector in the K direction. So that's vector unit K. And then FAO is the magnitude of FAO times the vector RAO divided by its magnitude. So vector mag RAO. And I'll do the same thing for FAB. And then finally the same thing for FAC. And then finally let's enter the equation for equilibrium. So that's just the sum of these 4 forces have to be 0. And at this point, if we haven't made any mistakes, which I don't think we have, and we solve, we can determine the forces in the cables and in the boom for this particular 500 pounds of weight. And you can see that I haven't exceeded the failure criteria for any of these members for 500 pounds. So what the question asks is, what's the biggest weight you can achieve? Or what's the biggest weight you can hold? And the way I do that is I have to increase W until I hit the failure criteria for the cables and then the boom. So the way I'll do that is I will comment out the magnitude of W that I specified, and instead I will one by one specify that the magnitude of the forces is equal to the failure criteria. So the failure criteria for the cable AB is 5,000 pounds. So I'm going to set the magnitude of FAB to 5,000 pounds, and now I can solve. And when I solve, I find out that cable AB is going to fail at W equals 3,000 pounds force. I can do the same thing for FAC. So now I'll set the magnitude of FAC to 5,000 pounds and solve, and I find out that in this case W is bigger. It's like 6,670 pounds. And then finally the boom will fail when it experiences a force of negative 8,000 pounds. At that point it will actually buckle. So if I set that magnitude and solve, I find that W is 3,840 pounds. So it looks like the W that's going to cause the first thing to fail is 3,000 pounds, and at that point cable AB will fail, right? So that's going to be kind of our weakest link, and that's the biggest weight that I can support. All right, so that's part A. Part B says this time we're going to specify the weight to be 1,000 pounds, but we're going to move the coordinates of point B and C, right? So they're going to be changed to B prime and C prime. So this is pretty easy. None of the governing equations change here. All that changes is I'm specifying the value of W, and then I'm going to change these coordinates. So if I have a professional version of these, I can make a new tab as I'm done here, and I'll label this new tab part B, and I'll just take all of my equations from my original solution, and I'll copy them and paste them into the new tab. And I have now basically an independent ease program that I can modify as I want. So I'm going to set the value of the magnitude of W to 1,000 pounds, and I'm going to go in here now and change the coordinates of B and C according to these new coordinates. So B is now 1408, and I guess C is 01818. And I should be able to solve now, and if I do that, I find that with these new fixing points and 1,000 pounds, I get cable AB has a 1,027 pounds force in it. Cable AC is 930 pounds, and then the boom is got a compressive force of 1,434 pounds. So that's the problem. I think the other thing to maybe do with this problem, because it's kind of interesting, is do a parametric study. So one interesting parametric study here, and let's go back to the original problem where we were trying to figure out, based on the failure criteria, what weight we could carry. One thing I can do is vary W in a parametric study, and as a function of W, look at the forces in these different members. So I'm going to make now a parametric table, and the parametric table is going to have in it W, the magnitude of W, and then the magnitude of FAB, FAC, and FAO. And I'll comment out the magnitude of W, and so I can run my table. I'll specify that it goes from some very low number up to some, I don't know, high value like 8,000 or 9,000 pounds, and I'll run my table, and you can see here visually that as I do that, as I increase W, all of these forces, the absolute values go up, right, which makes a lot of sense. If I were to make a plot now, so let's plot FAB, FAC, and FAO as a function of W, you can sort of see that what's going to happen is these different lines are going to hit their different failure criteria. So one failure criteria for the cables is 5,000 pounds. So if I put a horizontal line at 5,000 pounds across here, you can see that, yeah, FAB is going to hit that line before FAC, and so that's going to be the first cable that fails. And then for the boom, it's minus 8,000 pounds is the failure criteria, so I could put a vertical line across here at minus 8,000 pounds, and you can see that the boom's going to hit that failure criteria, but only after the cables have already failed. So that sort of agrees with what we came up with when we did this in part A.